So this is lecture 5. We're going to be discussing section 6.3, partial fractions, today and on Monday. So part 1, intro to rational functions. So first of all, irreducible polynomials. So irreducible, that is, it cannot be factored. That says factored. So there are two types. Linear, so ax plus b. You can't factor that any further. Now the graph of that is going to be a straight line. Crosses the axis once. That x value is going to be the number that causes that factor to be 0. There's just going to be one of those. So you can't break this down into smaller factors. And then irreducible quadratics. So ax squared plus bx plus c, where b squared minus 4ac is negative. Why does that matter? Well, when you have a quadratic and you're trying to find the values of x that cause this to be 0, you use the quadratic formula. And if it turns out that this term in the quadratic formula is negative, well, you have to take the square root of that, and you can't. So that means there are no x's that will cause this thing to be 0. So, for example, x to the 4th plus 3. I'm sorry, x squared plus 3. Well, that's a standard parabola that's been moved up 3 units. You know there are not going to be any x values that cause that to be 0. And if you try to use the quadratic formula to find some, you find that b squared minus 4ac is a negative number. So this is irreducible. Whereas x squared minus 6x plus 5, well, that can be factored as x minus 5, x minus 1. That's factorable. And sure enough, that parabola has x-intercepts at 1 and 5. So irreducible quadratics are ones that correspond to parabolas whose graphs don't cross the x-axis. Now what about other things whose graphs don't cross the x-axis? Well, let's turn around. Clearly, any odd degree polynomial can be factored. So y equals x to the 27th minus 13x to the 14th plus 87x cubed minus 2. Can you factor that? I don't know how to factor it, but it's an odd degree polynomial. One end goes up, the other end goes down, so somewhere it's got to cross the x-axis. So there's got to be a value of x that makes that thing 0. That's going to correspond to a linear factor that's made 0 when that value of x is substituted in. So this can be factored. What about something like this? X to the 4th plus 1. So that's a standard x to the 4th graph that's been moved up 1. Goes through 0, 1. There are no x values that cause that to be 0. So it doesn't have any linear factors. But observe, x to the fourth plus 1 is x squared plus radical 2x plus 1 times x squared minus radical 2x plus 1. Those are irreducible quadratics. So a big theorem, Gabriel probably knows the name of this theorem, but I don't, is that any polynomial can be factored into linear factors and irreducible quadratics. This can't be factored into any linear factors, but it can be factored. Its most basic building blocks are irreducible quadratics. Okay, rational functions. This is still part 1, introduction to rational functions. These are ratios of polynomials. So in other words, we have a function that's actually a p of x over a q of x, where these are polynomials. Now, a proper rational function means the degree of the numerator is less than the degree of the denominator. And an improper is when the degree of the numerator is greater than or equal to. Now, long division of polynomials. So how many of you learned how to do synthetic division of polynomials in high school? Raise your hand, like really high. Okay, how many of you still know how to do it? Keep your hands up. Yeah, exactly. So it's pretty useless. It's the coolest thing that you don't need to know. So the thing is, long division can always be used to rewrite an improper as a polynomial plus a proper. So in other words, a p of x over q of x that's improper can be rewritten as some polynomial s of x plus a rational function that's a proper one, r of x over q of x. So you just have to be careful about it and fearless. Let's do an example. Rewrite this x squared plus x cubed plus x squared plus 9x plus 10 over x squared plus 9. Rewrite it in that form. Well, let's just do long division. X cubed plus x squared plus 9x plus 10 divided by x squared plus 9. Now I don't skip any factors. So if a factor is missing, I don't skip any terms. So if a term is missing, I put it in as a 0. So in other words, this is x squared plus 0x plus 9. So then you have to figure out what goes here to make this term be the same as this term. Well, there has to be an x there, because x times x squared is x cubed. So then you multiply x by all these terms. So I get x cubed plus 0x squared plus 9x. And then you subtract the whole thing. When I subtract, I get x squared plus 0x plus 10. And then you do it again. You figure out what needs to go here to multiply this to match that. Well, that can just be the number 1. Has to be. So you multiply the whole thing. X squared plus 0x plus 9. And then you subtract the whole thing. And you end up with the number 1. Well, that's your remainder. So the conclusion is that that polynomial x cubed plus x squared plus 9x plus 10, sorry, that rational function can be written as x plus 1 plus 1 over x squared plus 9. So notice, improper, polynomial, proper. Part 2 of the discussion is, it's not a discussion, it's a lecture. I'm just doing all the talking. Sorry. Part 2 integrating rational functions. So, of course, we can always integrate a polynomial. So if you're given a rational function and it's improper and you want to integrate it, first thing you should do is rewrite it as a polynomial plus a proper rational function. Because you can always integrate a polynomial, and then you just got to figure out how to integrate a proper rational function. So the only issue is integrating proper rational functions. Because again, if you get handed an improper rational function and you're told to integrate it, you do long division to turn it into a polynomial plus a proper one, and you worry about integrating the proper one. So proper rational functions that we know how to integrate. Well, we know how to integrate 1 over x. That's ln of absolute value of x plus c. We know how to integrate 1 over x, ax plus b. We'd use substitution. And then 1 over ax plus b to some other power, say some power k. Well, you'd use substitution on this one, because because that's not a logarithm problem. That's going to be just a power rule function. So you're going to get 1 over ax plus b to the, let's see, to the k minus 1. So the power rule works weird for antiderivatives and for fractions of this sort, because it's in the denominator. Don't quote me on this. Don't put it on video on YouTube. Might be wrong. But the thing is, we know how to integrate all sorts of things of the form 1 over ax plus b. We can integrate 1 over ax plus b. We can also integrate 1 over ax plus b when it's raised to the kth power. So that doesn't scare us. We also know how to integrate 1 over x squared plus 1. That's arctan. We also know how to integrate 1 over x squared plus a squared. Here we have to use substitution. This becomes 1 over a arctan x over a. These are all details that are not obvious to you. You probably don't remember these. But I think it should be believable. This is substitution, and this is the power rule. And in general, if I have an irreducible quadratic, well, we can do a harder sub, and we get stuff involving arctan. I'm going to keep going with things that we know how to integrate. In general, our existing techniques can be used to integrate anything of the form, well, capital A over ax plus b raised to some ith power. Again, I've discussed some of those over there. Or an irreducible quadratic, ax squared plus bx plus c to the jth power, where this is irreducible. And in the numerator could be anything of the form capital Bx plus c. So any constants, capital A, capital B, capital C, that you want to put up here, and any little a and little b here, or any a, little b, little c, as long as this is irreducible, our existing integration techniques, even though it might be hard, will apply to these. So notice that each of these is something that is a proper rational function. So the question was proper rational functions that we already know how to integrate. So the question is, how do we integrate other proper rational functions that are not of that form? Well, there's a big theorem that any proper rational function so anything can be written as a sum of rational functions of this form. So of the form a over ax plus b to the ith power. I'm going to move this over, sorry. A over ax plus b to the ith power, or bx plus c over ax plus bx plus c, ax squared, to all this to the jth power, where this is irreducible. So again, any proper rational function can be written as a sum of these things. Oh, well, we know how to integrate those things. So a strategy for integrating any proper rational function would be get this form and integrate that. This is called the partial fraction decomposition. So the theorem says that any rational function has a partial fraction decomposition. So a strategy for integrating a proper rational function is to get the partial fraction decomposition, find the partial fraction decomposition, So in other words, you rewrite your given rational function as a sum of things that look like this, and then integrate that thing using our existing techniques. So integrate that decomposition. Let's call this PFD, the partial fractions decomposition. So integrate the PFD using existing techniques. So what we're trying to do in this section is expand our library of things that we know how to integrate. Okay, so in the remaining time, I want to do an example. Now, so again, this is a big theorem that any proper rational function can be broken down into a partial, it can be rewritten as a partial fraction decomposition. Okay, so part 3, we're going to do an example. Now, I said this is a big theorem. I said a while ago, well, I've said throughout the semester so far, I really like our book. I don't like that this really big theorem is not presented with some fanfare in the book. There ought to be a box around it, it ought to have a number, it had a name. It's a big theorem. It just appears in a paragraph. It just says we can always, there's a theorem that says we can always do this. Well, it should be a box. So part 3, and another thing that I don't like is that they don't attempt to articulate a method, a general method for doing partial fraction decomposition. They just present a bunch of cases. And they do a good job of that, but I think it's good to see if we could come up with some kind of overarching bulleted list. So I'm going to present a pretty useless bulleted list, but I think it's better than no bulleted list. So finding partial fraction decomposition. So start by factoring finding partial fraction decomposition for a proper rational function. There's no point in doing this for an improper rational function. We already know how to approach integrating those. You do long division to get rid of the improperness, and then you just deal with the proper rational function. So the first thing is factor the denominator completely into irreducible factors. So while I write this maybe useless bulleted list, I'm going to apply it to this polynomial, this rational function. 15x squared minus 6x minus 6 over x cubed minus x squared minus 2x. So notice that's a proper rational function. So let's apply that to this. We're going to factor the denominator completely. So 15x squared minus 6x minus 6 over, let's factor out the x. That leaves me with x squared minus x minus 2. Let's factor that some more. That's going to be 15x squared minus 6x minus 6 over x plus 1, x minus 2. Okay. I'm going to put this over here to the side so that it's all one line. Okay, build all basic forms, build a sum of all possible basic forms. Those forms that we already know how to integrate. These kinds of forms, using the denominator factors up to those powers. So using those denominator factors to those powers. Okay, well, so that's here. The basic form is going to be something over x. That's one of the basic forms. That's the highest power I can go, because that's the highest power here. Plus something over x plus 1 plus something over x minus 2. Yeah. It's not quite yet, right?
2 minutes until?
Yeah, so it's not time. So now we have to figure out the coefficients that match. So it turns out, so see the book. This is algebra, how to figure out values of A, B, and C that work. Turns out that that's 3 over x plus 5 over x plus 1 plus 7 over x minus 2. So, this is smoke and mirrors here. But there's a discussion of it in the book, and it's a good thing for you to read in the book. And so, if we apply that to the integral, we call this function f of x. If we're faced with the task of integrating f of x, again, integrating this thing that's not one of the forms that we know, well, that's going to be the same as the integral of 3 over x plus 5 over x plus 1 plus 7 over x minus 2. And that's 3 ln of absolute value of x plus 5 ln of absolute value of x plus 1 plus 7 ln x minus 2. So there's a lot that I'm rushing by here. The mystery of factoring is always scary. And then how on earth do you match these coefficients? How do you figure out these coefficients that work? Read the book. There are lots of examples. I can't dress this up. This is just hard. All right. So as Marcy said, we're out of time. Thank you all. Sorry this is so rushed. We're going to do this all day on Monday. So I'll see you on Monday. Put phones away, please. Remember, I don't want to see phones out.